Hello students. So in the last video we have discussed about the atomic spectra. How does spectra is forming? What is a spectra and how does atomic spectra are forming also, right? We have studied about the continuous spectra. That means continuous spectra means each color is merging into the another color. So we will get a continuous spectra, and if it is that of an atom, molecule or an ion, we will get the spectra won't be a continuous one. It will be a lot of lines over there. So we call such spectra as the line spectra also. So in the last video we have discussed about the continuous spectra as well as the line spectra or atomic spectra, right? We can just recall whatever that we have studied in the last video, right? The main point that I discussed over here, how does atomic spectra are forming, right? Atomic spectra will be forming when an atom absorbs energy, any kind of energy. So if an atom absorbs energy in any kind, what will happen over here? The atom, the electrons present in the atom will get, it will be absorbing the energy. So when it's absorbed the energy, it will be rotating in a particular stationary state, right? We have discussed in the Bohr's atomic model. The first point they are telling is that electrons are revolving around the nucleus in a stationary states, right? So that particular stationary state have a particular energy over here. So when an electron absorbs the energy, what will happen? The electron will jump from the lower energy state to the higher energy state. But the higher energy state means we call it as the excited state. The lower energy where it was really occupying, we call them as a ground state. So it will get excited from the ground state to the excited state. But excited state was not at all stable. So what they will do? They will come back to the ground state by emitting the radiations, by emitting any kind of electromagnetic radiations, right? So when it is emitting electromagnetic radiation, it won't emit out all the electromagnetic radiation. It will emit out only a particular radiations of a particular wavelength or frequency only. That's the most important thing. So each atom has a unique its own spectra, because each atom has the ability to give out the electromagnetic radiation of a particular wavelength only. Some radiations it will be absorbing, right? And when it will go jump into the higher energy level, and it will come back to the lower energy level by emitting out the radiation. So thereby we will get two spectrums, emission spectrum and the absorption spectrum. Actually atomic spectrum means it is an emission spectrum also only, because we are detecting the radiations which are emitted by the atoms, right? Emitted by the atoms when it is coming back to the stationary state. So when we look at the emission spectrum, there will be a lot of dark spaces over there. So what does that dark spaces indicates? Yes, it is the absorption spectrum. That is the radiations which are absorbed by the atom. It will be seen as the dark spaces over there. Okay, so that is about the atomic spectrum. So in this video we will be studying more about the Bohr's atomic model of hydrogen atom, right? So we'll study more about this. Some more postulates are there with the Bohr atomic model. We will discuss that in this video. Plus we will study about the atomic spectra of hydrogen atom also. Since Bohr atomic model, it is specially for the hydrogen atom, we are studying about the spectra or the atomic spectra of the hydrogen atom too. Again, the hydrogen atom will it has a capacity to form a spectrum, right? We will study about that in this video. Okay, by the hydrogen atom, the spectrum is divided into 5 series. Lot of series are there. Lot of series means electromagnetic radiations include lot of radiations, right? It will have a UV light, ultraviolet area is the, then infrared area is the microwaves, radio waves, right? So many rays are there which is included in the electromagnetic radiation. So depending upon which all radiations the hydrogen atom is emitting out, we will be depending upon that we have different series for the hydrogen atomic spectra. Okay, we will study more about the hydrogen spectra in this video, as well as the more postulates in the Bohr atomic model of hydrogen atom too. Okay, so as I told you, this current academic year we are starting from the Bohr's atomic model of hydrogen atom plus as I told you, we are starting from page number 42, but still no, when we are studying about the Bohr atomic model, lot of terms are coming, right? So we need to study that term also. We need to study about the spectrum, right? So that is why I just turned the page and started from the atomic spectra. What is atomic spectra, and what is a atomic spectra of hydrogen atom? That is why I included that topic also. Actually, that topic is not mentioned in your syllabus, but still it is needed for you to study the Bohr atomic model of hydrogen atom. So that is why I included that too. Okay, so study properly whatever that I am teaching. You have to study these all things that you are it is needed for your chemistry studies and all. But the other topics that Ishar sir will discuss when he is taking the entrance classes, but I won't be considering that for your board examinations. But the topics which are needed, I will be teaching. Okay, so study properly, write the notes properly, and one more thing that I need to tell you is that or in your WhatsApp group, class 11 WhatsApp group, so many messages are coming. It is admin only group, so whatever that messages that is coming in that group is meant for you. Okay, as a message for you, so you should have a continuous track on what is happening in that particular group. Okay, so whatever the messages is coming, it's a message for you. So you have to read it, you have to understand it, and you have to understand the current situation also. I have given one assignment last week. I have given so many days for you to complete that assignment too. Actually, it's only a 1 hour, less than 1 hour duration is needed for that particular assignment. But still, I gave you a lot of time, so I want you to make it as a perfect one. Okay. But the problem is that so many students haven't done it on correct time. Then I send the messages through our WhatsApp group saying that these all students haven't done that particular assignment. Still, I didn't get the 1, 2 or 3 students assignment were missing from that. The next thing is that, as I told you, you should not join in the Google Classroom with your parents' account. If you're joining with your parents' account, what's the problem is that instead of your name, your parents' name is coming. It will be difficult for we teachers to sort it out. Okay, so so when you are seeing this video at that moment itself, try to unenroll from, just remove from your parents' account from there and log in only using your own account. Okay, so still I can see lot of parents' name written over there. So I'll be removing all those accounts, but all the notes, everything I'll be posting in the Google Classroom only. So log in using your own name itself. All the other accounts I will remove today itself. When you're seeing this video, that will be removed. Okay, and don't tell me that you cannot upload the notes or images through the Google Classroom. You have to practice that. There will be slight network issues are there, means you will be there will be lagging for you to upload it. Otherwise if you can upload it in the WhatsApp, you can easily upload it in the Google Classroom also. Okay, the works which is given to you, you must do it on correct time, because 100% cooperation is needed from your part also. Okay, otherwise we cannot go further. The current situation, the situation is getting worse only. So our teaching mode is like this. Okay, so you have to understand that truth. You have to your full cooperation, 100% cooperation is needed for this attempt. Thank you. Watch this today's video, complete the notes, and if any type of doubts is coming, contact me. Okay, thank you.
So let us study how does hydrogen atom is producing its own line spectrum. Okay, so as I told you, some sort of energy should be applied to these molecules, atoms or ions. So what will happen? This will absorb the energy and will get excited. It will get jumped to the excited state, right? It will get jumped to the excited state, which is of a higher energy. From where do it is moving to the excited state? Excited state means which is of the higher energy, right? From the ground state. Okay, so a molecule, atom or an ion, it will be in its ground state initially. Okay, so what it will do, it will absorbs energy. It will absorb energy, and what it will do, it will get excited to the higher energy level. We call that higher energy level as the excited state. Here what will happen, excited state, it is not at all excited state, that state is not stable. So what it will do, it will come back, to its ground state by emitting certain radiations. What radiations it will emit out? Electromagnetic radiations. It will emit out electromagnetic radiations. Okay, it will come back to the ground state by emitting electromagnetic radiation. So each molecule or each atom has a capacity to emit out electromagnetic radiations of a particular frequency. Okay, a particular frequency or particular wavelength only. Okay, so that is what we are told, that each atom's spectrum is different. So each atom has its own unique spectrum. So each atom has a capacity to emit out electromagnetic radiation of a particular frequency or wavelength only. Okay, so this is the line spectrum. This is and it is forming not the continuous spectrum. We have studied that the atomic spectrums are of line. It has a lot of discrete lines over here, right? So it is forming line spectrum only. So this is a diagrammatical representation of the line spectrum of the hydrogen. Okay, so from here it is understand that you can see a lot of series is written over here, right? You can see Lyman series, right? Lyman series. So these series are named after their discoverers. Whoever has discovered these spectrum, it contains lot of several series of lines are there. So it is named after their discoverers only. Lyman series. Why it is given as a ultraviolet means the Lyman series, all the electromagnetic radiations are coming under the ultraviolet region of the electromagnetic radiation. Okay, then you can see the Balmer series over here, Balmer series, then Passion series over here. Like that, different series are there. So there are mainly 5 series are seen on the hydrogen spectrum. What are the 5 series that we are seeing in the hydrogen spectrum? Is the Lyman spectrum. Lyman spectrum, as we have discussed. Then we have the Balmer series. Then we have Passion series and Bracket series and Fund series. So these are the main 5 series of the electromagnetic radiation that we are seeing in the line spectrum of the hydrogen. Now these series are named after their discoverers also. Okay, the next thing is that what is this Lyman, Balmer, Passion and Bracket and Fund series are known as. Now look it over here. So the first one is the Lyman series. So Lyman series means those series which are discovered by the scientist Lyman. Here it is given as n is equal to 1. What is this? N indicates the number of orbit. So n is equal to 1 means the electron was in the first orbit. So when n is equal to 1, what is it? It is absorbing the energy in some way, some electric discharge or something. If it is subjected to fall on the hydrogen molecule, so it is absorbing the energy. So from it is absorbing the energy, right? So from which orbit to which orbit the electrons are moving. So depending upon that, we have different series over here. So first you look at the Passion series. So Passion series means it is coming from n is equal to 6 to n is equal to 3. Right? So that means this Passion series means electron is getting excited to the 6th orbit and it is coming back to the 3rd orbit. Okay, so now look at, and all the electromagnetic radiations which is emitted out from it is coming on the category of infrared area. Then look at the Balmer series. So Balmer series means the electromagnetic radiations are coming in the visible region. That means it can form the Webjor colors. So Balmer series means the electrons are getting jumped from Light violet color. You can see the violet color over here. Violet color will have a form if it is jumping from n is equal to 6. N is equal to 6 to n is equal to 2, second orbit. And if the transition is occurring from n is equal to 5 to 2, then we will get a blue color. And then if the transition is happening from n is equal to 4 to n is equal to 2, we will get a green color, and from n is equal to 3 to 2 we will get the red color also. So depending upon from which orbit to which orbit the transition is occurring, we have different series over here. So that is what it is given over here. Lyman series, it is n1, that means it is coming back to the first orbit. Then it can jump from second, third, fourth, fifth, or anywhere like that. Okay, so that we call it as a Lyman series. Then Balmer means second, so it is coming back to the second orbit from the upper higher energy orbits. Okay, so likewise we can find out the different series present in the hydrogen spectrum. Now, if we are representing these spectral lines in terms of wave number, suppose if we are representing these series in terms of wave number, what is wave number? What is wave number? How can we represent the wave number? Wave number is the number of waves per unit distance, or we can say that it is a reciprocal of wavelength. It is a reciprocal of the wavelength or number of waves per unit distance. We call it as a wave number. So if we are representing the spectral lines in terms of wave number, it is seen that all these series are now following a general expression. That is, wave number we are representing as nu bar is equal to Rydberg constant RH. Rydberg constant we are representing it as RH into 1 by n1 square minus 1 by n2 square. What is the unit of it? Centimeter inverse. So unit of the wave number is centimeter inverse, right? So number of waves per unit distance, or the reciprocal of the wavelength, right? So if we are representing these spectral lines in terms of the wave number, we will get nu bar is equal to RH into 1 by n1 square minus 1 by n2 square, where n1, what is n1? It is 1, 2, etc. What will be the n2? N2 will be greater than n1, right? So n1 plus 1 or n1 plus 2, because it is an excited state. So this is a ground state and this is an excited state. So n2 is equal to n1 plus 1 or n1 plus 2, etc. And what is this Rydberg constant RH? The Rydberg constant RH has a value. It is constant. The value is 109,677 centimeter inverse. This is a constant value. We call it as the Rydberg constant. We call it as the Rydberg constant for hydrogen atom. Rydberg constant for the hydrogen atom. So this is what the line spectrum of hydrogen is. The spectral lines of hydrogen, we are divided into separate series. Okay, so these are the something that you need to remember about the line spectrum of hydrogen. So when the hydrogen molecule is excited by passing electricity or whatever, so hydrogen molecule is absorbing the energy. So what they will do? They will go to the excited state. Excited state orbit we are representing as n2, and that is now stable, so it will come back to the ground state by emitting electromagnetic radiation. So in which area the electromagnetic radiation is falling, in which category it is falling, depending upon that we have different series for the line spectrum of hydrogen. If the electromagnetic radiation is coming under ultraviolet region, we call them as a Lyman series. If it is coming in the visible region, so visible region means it is a Balmer series. If it is coming under the infrared, we have the Paschen series, bracket series, and Fun series. Okay, so depending upon from which orbit, which excited state to ground state it is undergoing the transition, we have different series over here. Okay, so if you are representing this line spectrum of hydrogen in terms of wave number, it is obeying the equation u bar is equal to RH into 1 by n1 square minus 1 by n2 square, where n1 is 1, 2, etc. So n2 will be the excited state, so it will be greater than n1. So it will be n1 plus 1, 2, like that it will go on like that. What is the value of Rydberg constant? It is 109677 centimeter in. So this is for the hydrogen spectrum, line spectrum of the hydrogen atom. So let us study more about the Bohr model of hydrogen atom now. So in the last class we have discussed about the main postulates of the hydrogen atom. So we can expand much more about the Bohr's model of hydrogen atom, and we can study more about the Bohr theory of hydrogen atom now. So the first postulate, so we have discussed about the main 4 postulates of the Bohr model of hydrogen atom. Now we are expanding more complicated and more information that we are getting from the Bohr's atomic model of hydrogen atom is that. So the first point we are stating is that suppose this is an atomic model. Suppose a nucleus is there at the center and the electrons are revolving around the nucleus through an orbit, right? So we can number this orbit. Okay, so the orbit we are numbering as n, small letter n. So the orbit which is closer to the nucleus, we will number it as 1. Okay, we will number this as 1. So the second orbit which is staying next to the first orbit, we name it as 2. Likewise it will go on, then it will have 3, 4, 5, 6. Okay, so the orbit which is closer to the nucleus is 1. So n has a value of 1, 2, 3, etc. Okay, so the stationary states, we can say that the stationary states, or we call it as the energy levels, right? The stationary states for electron are numbered. It is numbered as n is equal to 1, 2, 3, etc. And these integral numbers, or these integral numbers are known as principal quantum numbers. These numbers we call it as the principal quantum numbers. Okay, we will study more about the quantum numbers in this chapter. So n is equal to 1, 2, 3. This n we call it as the principal quantum number. So as I told you, and in nucleus will be there at the center and it is surrounded by certain orbits. So it is numbered as 1, 2, 3, etc. Okay, so that is the first point. The second point, what is the second point, is stating that we can measure the radii. We can measure the radii of the stationary states. Okay, we can measure the radius, that is the distance from the nucleus to the orbit. Okay, so suppose we need to find out the radius of the n is equal to 1, the first orbit, then it will be the distance between the nucleus and the first orbit. So n is equal to 2 means the distance between the nucleus and the second orbit. So I can measure the radii of the stationary states. So it can be represented as Rn. Rn is equal to n square a0. Rn is equal to n square a0, where A0 value is constant. A0 is 52.9 picometer. A0's value is constant, so we call it as the 52.9 picometer. Okay, so normally the electron present in the hydrogen atom will be it will be seen in the first orbit only. Okay, we can measure the radius of that orbit. N is equal to 1, 2, 3, wherever that electron is situating. So suppose if we are considering the hydrogen atom, the n will be equal to 1, right? If hydrogen has only one electron, will be in the first orbit. So what will be the radius of it? So it will be r1 is equal to, n is equal to 1, right? So 1 square into 52.9, so we'll get the answer as 52.9 picometer. Suppose I need to measure the radius of the second one, that is n is equal to 2, second stationary state. So R2 will be is equal to 2 square into 52.9. We'll get the answer. So likewise it will be continuing. So we can measure the radii of the stationary state. It is expressed as Rn is equal to n0, Rn is equal to n square into A0, where A0 value is constant. We call it as the 52.9 picometer. So let us check the next point in the Bohr's theory of hydrogen atom. So the next theory is about the energy. Next theory is related with the energy of its stationary states. We can measure the energy of each stationary state. We know that the orbit which is closer to it will be have lower energy. So when it is going away from the nucleus, the energy will be increasing also, right? So what will happen? We can represent the, we can express the energy of the stationary state by using an equation. En is equal to minus RH into 1 by n square, where n has a value 1, 2, 3, etc. So En is equal to minus RH into 1 by n square, right? So why we are using the minus sign over here means always the energy will be getting losing when the electron is getting excited, right? So that is why in order to make the energy as a positive one, we are using the negative sign over here. What is this RH? We have seen it, right? It is the Rydberg constant. RH is the Rydberg constant. What was the value of the Rydberg constant? It is not the same value that we are used in our wave number. So here the RH is, we call it as the Rydberg constant. Okay, so Rydberg constant value is 2.18 into 10 raised to minus 18 joule. Okay, so we have find out the Rydberg constant value for hydrogen atom. So what was that? 109677 centimeter inverse, right? So this is the Rydberg constant value. RH is equal to 2.18 into 10 raised to minus 18 joule. Okay, so energy of the lowest state, we call it as the ground state. So when the electron is getting excited, it will go to the higher energy states. So we can measure the energy of each orbit, right? So what will be the E1? E1 will be equal to minus RH into 1 by 1 square. We'll get 1 by 1 square. N is equal to 1, right? So we'll get the answer as minus 2.18 into 10 raised to minus 18 joule, right? Likewise, for each stationary state, we can measure the energies also. Okay, so we can see that the energy of the stationary state is increasing. So the representation of the energies of different orbits. So the representation of the energies of different orbits or the stationary states. So the representation of the energies of the stationary states, we call it as the energy level diagram. Energy level diagram. So energy level diagram is the representation of the energies of the each stationary states. Okay. So these are the main three points that we need to consider in the Bohr theory of hydrogen atom. So the first one is, we can number the stationary state for the electron. We can number it as 1, 2, 3, etc. We call them as the principal quantum numbers. We can measure the radii of the stationary state. We can measure by the using the formula Rn is equal to n square into A0. Then we can measure the energy of the stationary state by using the formula En is equal to minus RH into 1 by n square, where RH is the Rydberg constant. There's a value 2.18 into 10 raised to minus 18 joule. Okay, so we are using the minus sign over here. So what will happen here means normally the energy will be emitted, and if it is emitted means the energy will get lower. So that is why we are using the negative sign in this equation also. But the same Bohr theory we can represent, we can use the same Bohr theory for the other atoms also, other elements also. We can using the same Bohr theory of hydrogen atom if it contains only one electron. So we can use this Bohr theory of atom for the other ions also. It would be ions with the one electron only, with one electron, just like the hydrogen atom. Hydrogen atom has one electron. Like that, same other ions which is having the one electron, we can apply the same theory for the other ions which is having one electron. Okay, for example, helium plus He plus, right? Helium atomic number is 2. It has 2 electrons in its outermost shell, right? So plus sign indicates no electron is lost. How many electron is lost? 1, right? So it has 2 electrons, so 1 electron is lost means it contains only 1 electron, just like the hydrogen atom, right? Then what about lithium? Li2 plus. Then lithium means it has 3 electron in its outermost shell, but 2 plus, that is ion, so it has lost 2 electrons. So how many electrons it will have? It have only 1 electron in its outermost shell. So likewise lot of ions are there. Beryllium, Be3 plus. Likewise certain ions are there which is having the, just like the hydrogen atom, only 1 electron is there in the outermost shell. Okay, for that cases also we can measure the energy of the stationary states. Okay, for these ions also we can measure the, we can say that hydrogen like species, we can measure the energies of the stationary states of the hydrogen like species also, but we just need to change those equations. So here we have used the 1 over here, right? En is equal to minus RH into 1 by n square. 1. So instead of 1, what you need to do is, we need to use, instead of 1, a slight difference will be the En is equal to minus RH into, instead of 1, we will be using Z. Z is the atomic number square divided by n square. Okay, joules. So this is the representation we are using for the hydrogen like species in order to find out the energies of the stationary states of the hydrogen like species. So instead of 1, we will be using the Z square, whereas Z is the atomic number. So we can find out the radii also. We can find out the radii also for such hydrogen like species. So here what will happen is, here also we will have a certain change. We say that Rn is equal to 52.9, that is the A0 into n square, that much we have here, divided by Z. What is that Z? Again it's the atomic number. So Rn is equal to 52.9 into n square divided by Z, where Z is the atomic number. So this is the continuous explanation of the hydrogen Bohr theory of hydrogen atom.